Our second talk is going to be a virtual recording version, but DGO. He worked on static analysis of Android apps for malware detection at Google until recently. Now he works on compiler optimization and at TikTok ByteDance. All right, so let's start his talk. All right.
Hi everyone, I'm Girish Mururu. I'm currently at ByteDance TikTok, where I work on compiler optimizations. This work was done along with Vincent, Professor Ada, and Professor Santosh Pande while I was at Georgia Tech. I'm sorry that I'm not presenting this work in person. I hope the recording does a fair job in presenting this work. PinIt, influencing OS scheduling via compiler-induced affinities. Recently, there have been varieties of CPUs and SoCs which have been developed with ever-increasing number of cores, but these cores have shared resources such as shared memory, shared buses, I/O, etc. And then there is this set of applications, especially in media, image and video processing application, vision applications, machine learning, simulations, etc., which are the new workloads that have become quite omnipresent, and these applications are very sensitive to these shared resources such as caches, etc. Currently, the OS scheduler tries to efficiently schedule multiple processes while managing the shared resources effectively. It tries to be fair by treating all processes similarly and does load balancing to effectively utilize the resources, and also has some degree of affinity for the processes to utilize what they had done previously. However, the scheduler is almost completely aloof to the individual requirements, resource requirements of processes. And hence it also treats all these processes which are in execution in a similar manner. An example of such a scheduler is the current scheduler in Linux, which is the completely fair scheduler. So CFS, the completely fair scheduler in Linux, treats all processes similarly, although every process has different resource requirements. And the requirements vary across different processes, and not just across processes, but it also varies within the process. Like dynamically, there can be different kinds of resource requirements within different phases of execution of the process. However, it's not the fault of CFS, because CFS, or the scheduler CFS, does not know what the process wants. Then who knows what the process wants, right? Well, the compiler can analyze the requirements of the process statically. However, traditional compiler optimizations have been limited to optimizing individual applications. There have been tremendous progress in improving performance of single and multi-threaded applications. However, global compiler optimizations across applications is infeasible due to ever-changing dynamic runtime environment and different phases of different applications in execution. So compiler and scheduler stacks have largely evolved standalone. So here, the question is whether bridging this gap can help us improve the performance of these individual applications by some kind of knowledge for the scheduler about the processes. Right? So here we look at the problem of process migrations, where given a huge number of processes, the CFS first schedules these processes onto the available cores. So when there is no more cores available for a scheduling process, it preempts an already running executing process, puts it back to the ready queue, and then schedules a different process. However, it keeps doing this, and then when it's the time for the process to execute again, then it might the CFS might not schedule it back onto the same core on which it was executing. So this means the process has lost its already warmed up cache. And this problem is more severe if the process is scheduled onto a different socket, because now it has to warm up all different levels of caches. So CFS actually tries to maintain some cache affinity for the processes, but when it comes to load balancing, it prioritizes machine utilization much more than providing the process with the same with cache affinity, right? So it affects processes adversely and in terms of performance, because it has to it incurs a lot of cache misses. But and especially when if the processes are executing some cache intensive regions, then this effect is much severe. So to mitigate this, a process can be actually pinned to a core, but then completely pinning a process to a core adversely affects the flexibility of the scheduler in terms of load balancing to achieve optimal or a better performance for all the processes as an ensemble. So towards this, we have developed PinIt to basically minimize the amount of pinning to have enough flexibility for the scheduler to do its load balancing to manage the resources effectively, while allowing for the cache intensive regions of the processes to not to be executed on the same core and not be migrated while it's executing such a. The PinIt framework involves analyzing the input program to determine the regions within the program that must be pinned, and then perform optimizations to reduce the number of pin-unpin calls to the runtime library and then the underlying OS. The generated binary basically uses the runtime library to then influence the OS to effectively utilize the cores. We look at loops within the application, as loops tend to define phases of execution with different memory requirements. So we developed some terminology to help reduce the loops that require pinning. First is reuse. As common, reuse is basically the access of the memory that was already accessed previously. And then reuse distance is basically the number of loop iterations between such accesses. So now, higher the reuse distance, higher the number of cache misses if the process that was executing the loop was migrated. For example, if the loop contains the statement a of I equal to a of I minus 1, then when this process is migrated while executing this loop, after migration, this loop would incur one cache miss for all next n iterations, resulting in n cache misses. We then define unit memory reuse as the amount of memory reuse that is generated by each unique memory access. This helps us to differentiate those loops that will incur huge number of cache misses after migrations versus those that doesn't. For example, the Fibonacci loop here incurs only 4 cache misses, incurs only constant, can incur up to maximum of 4 cache misses when it's migrated, which is constant, compared to the summation loop, which can incur on average m by 2 cache misses when migrated for the execution of the statement 3 in the code. So basically, unit memory reuse captures the amount of this cache misses that is incurred once it's migrated. Then memory reuse density is a metric for us to guide the size of the region that is being pinned versus the amount of unit memory reuse that is obtained. So this metric basically determines the trade-off between benefits of memory reuse versus loss of scheduler flexibility. We perform optimizations to reduce the number of dynamic pin-unpin calls. The pin-unpin calls are instrumented across the loops, the outermost loops interprocedurally. Then, if these loops are still within the interprocedural loops, we hoist these pin-unpin calls outside the such interprocedural loops and also outside other call sites. For example, in the pin-unpin call within function foo outside the loop is hoisted across the call site in function boo and across the interprocedurally outermost loop function within function goo. We also perform loop splitting in a greedy fashion to improve the memory reuse density and remove any instructions that are not dependent on the instructions that generate memory, that contribute to memory reuse density. We also merge consecutive pin regions to avoid any intermediate unpin and pin calls. The runtime library maintains a shared bit mask of all the processes, and whenever a pin request calls comes in for a particular processor or particular code, that particular bit is set, and then any subsequent request for pinning on the same core is rejected. Basically, we allow only one process to be pinned to a given processor or a core. And then we use sched set affinity and get affinity Linux APIs to basically pin and unpin a process to a core. And we use shared memory semantics basically to maintain the shared bit mask across the processes. So now the processes are under CFS. The processes are preempted, where there are no more available cores for other processes to be scheduled. So even if a process was to be pinned to a core, if it was preempted, then the next process that would execute on the same core would basically pollute the cache of the previous process, of the pinned process. And when the pinned process comes back, it would still not find its cache. So to avoid this problem, we basically under PinIt, we perform non-preemptive scheduling so that it doesn't lose its cache when preempted, or it's not preempted in the first place. So Linux provides FIFO scheduling, which is the same as non-preemptive scheduling. The environment on which we run the experiments was overloaded with 50% more processes than the available number of cores. The underlying OS was Linux, and our baseline was basically priority CFS. I'll get to it. And then We use media bench consisting of media encoders and decoders and San Diego Vision based benchmark suite, which consists of vision processing applications as our benchmarks. And we created a mix of high priority processes and low priority processes with basically decoders and vision applications that are latency sensitive as high priority processes. And then these high priority processes were managed by PinIt framework, and the low priority processes did not involve any pinning. And the goal was to improve the performance of high priority applications while also completing the low priority applications, execution of low priority applications as fast as it could in the baseline. So as I said, we divided the benchmarks into high priority and low priority set. The encoders are usually on the slower path on the media streaming domain and can be run as low priority processes. The decoder, on the other hand, are customer facing and are latency sensitive. And similarly, the vision applications are also latency sensitive. So we use a heterogeneous mix of decoders as high priority processes and also a homogeneous mix of San Diego Vision based benchmarks as high priority process. For all these heterogeneous and homogeneous mixes, the set of encoders were run as a low priority processes. We compared PinIt primarily against priority CFS as baseline, in which the high priority processes are assigned lower nice values, which means these are scheduled with higher priority. And then the rest were basically assigned a lower priority. The encoders were basically assigned lower priority. The latency, which is the mean completion time of higher priority processes, improved considerably in PinIt compared to baseline priority CFS, with as much as 45% on 16 cores and 13% on 8 cores for media bench, and 8 and 9% for 16 and 8 cores for SDVBS. The entire batch consisting of high and low priority processes completed as fast as priority CFS compared to in PinIt completed as fast as priority CFS, with media bench on 16 cores performing 23% better than priority CFS. The high priority completion time on average for overall the mixes for media bench was better. It almost was 16% better for 8 cores and almost 2x better on 16 cores. We saw there was a decrease in the whole entire cache misses for all the mixes put together on both 8 cores and 16 cores. And the number of migrations was also reduced with PinIt. For San Diego Vision based benchmark, we saw about 35% improvement on 8 cores on average and 23% on average on 16 cores. The migrations reduced a lot, but the cache misses did not improve much for San Diego Vision based benchmark. However, we saw a huge reduction in number of page faults. We also compared PinIt against just non-preemptive scheduling and non-preemptive complete pinning. And we saw that PinIt as required gets the best of both worlds. It performs better than both. And in case of media bench, 16 cores, at least it is at least as good as the best among the two. So this means PinIt allows for scheduler flexibility while disallowing the unnecessary process migrations. Overall, MRD, memory reuse density, allows to look at all three parameters and guides towards increasing scheduler flexibility and data locality while keeping the overheads to low. This is all from me. I'm happy to answer any questions.
All right, Girish, are you here?
Yes.
All right, sounds good. Is there any question from audience? All right. Excuse me.
This is the questions about your presentation. So PinIt is basically the process is pinned to one particular process, a processor. No process migration is not allowed. Is that correct? So
Yes, correct.
So let me repeat my question. So PinIt won't allow the process migration to the other processor.
That is only for a limited amount of time within the region for which it is being processed.
All right, the audio is not very great, but any other question? All right, let me ask one. In your analysis, you actually did some loop analysis. How do you handle the loop with a dynamic bounds, where the number of iterations is determined at runtime?
Right. So for such kind of loops, we did two kinds of experiments. One is having like loop count or as a given tip count for each loop, and also we did another experiment where we based on profiling, we found that in both cases the same loops and performance did not thus the performance did not differ. For profile driven way, which would be much better approach.
Even though the audio condition was not really great, it's good to hear the answer. So let's thank the speaker again. Thank you.